In this video, I talk about eigenvalues and eigenfunctions of differential equations. For illustration, I will again use an ODE of the Euler-Cauchy type. It's similar to the one in the previous video where I talked about the boundary value problem. So let's step through this script. We start by setting some defaults, clearing the workspace, closing the previous figures. The problem is now to search for non-trivial solutions to the equation in line 7, which reads x squared times y double prime plus 3 times x times y prime plus lambda times y equal 0. And lambda is a free parameter, and we search for non-trivial solutions with homogeneous boundary conditions. So the solution has to be 0 at both ends of the interval, but we are allowed to adjust the free parameter lambda to obtain such a solution. Since there is a free parameter, we need one more boundary condition to fix the solution, and I've chosen the boundary condition indicated in line 10. So the function value is 0 at both ends of the interval, which runs from 2 to 8, as in the previous video. And in addition, I want the slope at 2 be equal to 1. So y prime at 2 is equal to 1. These are the three boundary conditions the solution has to fulfill. The adjusted value of the free parameter is called an eigenvalue of this equation, of this ODE, and the solution to this eigenvalue is called an eigenfunction. So let's start by defining the equation in symbolic form. This is very similar to the previous video. We have now a symbolic parameter lam, which enters into the definition of the equation in line 14. Line 16, we define the initial conditions y of a, y of b, and y prime of a, which are 0, 0, 1, respectively. The interval is bounded at 2 and at 8. Just like in the previous video, we now convert to a first-order system. But we have to take care that the resulting function handle, fh, in line 23, is now a function of 3 parameters, of 3 inputs, 3 arguments. F, the right-hand side, the variables y and y prime, and the free parameter lambda. This is important, otherwise the following code will not work. So fh, the function handle, has to be a function of lambda as well. Now we can define the function handle that computes the initial guess of the solution. This also may depend on lambda. I have chosen the following. My initial guess of the solution is just a parabola through the endpoints with the correct slope, and I divide by lam to have some variation in the initial condition, and the second row of this function handle is the derivative of the first row of the first element. So we have a parabola in the first row and a straight line in the second row. The next step is the definition of the function handle that describes the residuals at the boundaries. This is now a 3-vector since we have 3 boundary conditions. This should read boundary conditions So let me save this and start again. So we can skip the next lines. Okay, here we are. We've defined the y_init function handle. Now we have to define the bcres function handle. If we compare it to the function handle in the previous video, we see that, where are we? Here we are, for instance. In the previous video, in the boundary value problem, this function handle was a function of ya, which is y and y prime at a, yb, which is y and y prime at b, and the initial values that we have defined. In the eigenvalue problem, this also has to depend on the free parameter lambda, which is here in the third position. Well, it's not actually used in the computation of the residuals, but it has to be there as a parameter, an input argument of this function handle. So we continue now by defining the grid for the initial guess, and we have to have some initial guesses of the eigenvalues. I've chosen 1, 10, 20, and 50 just for the purpose of demonstration. So let's see what we obtain. So we loop over these guesses. We create the structure sol_init by invoking the function bvp_init. And in contrast to last time, this now also has a third argument, which is just the current guess of lambda. Now we are ready to invoke the solver. The solver has, again, three arguments: the function handle, then a function that computes the residuals as a function of ya, yb, and lambda. So we create this anonymous function which takes the result of bcres, our function handle, as a function of ya, yb, lambda, and our initial conditions y0. And the third argument is again sol_init. So we invoke the solver. Since there are neither warnings nor error messages, the solver has converged to a valid solution. This is not always the case. I will show an example later where the solver fails to find a valid eigenfunction. Now let's extract the quantities we need from the structure sol. We first subtract the x values, then the solution, then the first derivative, and finally the second derivative. If we look at the structure sol, we see it has also field parameters, and this is just the field where the eigenvalue, the free parameter, is stored. We can extract this eigenvalue from this field and display its value. It's about 6.1356. Now let's proceed to the graphical representation of this eigenfunction. Let's plot the solution. This is the eigenfunction. We plot a title. So here you see the ODE, the initial conditions, and the eigenvalue to this eigenfunction. We compute the left-hand side of the equation using the just found eigenvalue, and this should be identically equal to 0, and as you can see, it actually is. Right, so we have found one eigenfunction and the corresponding eigenvalue in the vicinity of 6. Now let's try our next guess. Let me put a breakpoint here so we can skip the entire loop and just have a look at the results. Our next guess is 10, so let's look for a solution with this guess, and we find the same one. We again find the eigenfunction to the eigenvalue 6.1356. Next guess, 20. We find a different eigenvalue, 21.5423. And you'll see in figure 3 the corresponding eigenfunction. The left-hand side is again identically equal to 0. Right, next guess, the final guess is 50. What do we see with a guess of 50? We find again another eigenvalue, about 130, 129.4, and the eigenfunction turns out to be an oscillating function of x. So we have found 3 different eigenvalues and the corresponding eigenfunctions. As I said before, there is no guarantee that a valid solution is found. This may depend both on the guess of the eigenvalue and on the guess of the eigenfunction of the solution. So let's try a different guess. Well, let's try 1000. Let's see what happens. Well, it does find an eigenvalue, but we already know this one. It's 21.5423. So let's be a bit more courageous. Let's put 10,000. Yeah, in this case, the solver does not converge to a valid solution. It says unable to meet the tolerance without using more than 5,000 mesh points. And you see that this solution looks very strange. So it's obvious that this run has not converged to something that is a valid eigenfunction. There can also be different types of problems. Let's try 10 to the 6 as a first guess of the eigenvalue. In this case, we get an error message. The script aborts, and the problem is obviously a singular Jacobian matrix somewhere deep inside the algorithm. So in this case, it's not able to continue the computation and aborts with an error message. So you see that finding valid eigenvalues and eigenfunctions is also kind of guesswork, unless you know from theoretical principles what the eigenvalues are and how the eigenfunctions should look like. Also, if we start with a guess of 100, I would expect, or we would expect, to converge it to the eigenvalue of 129 that we have found before. Let's try. It does converge, but not to 129, not to the nearest eigenvalue, but to 21.5, which we also have found before, starting from a guess of 20. So there is no guarantee that an eigenvalue is found, or even that if an eigenvalue is found, it's the closest one to the guess. So let's try again our initial guess, which was 1, 5, 20, 50. And we find 3 different eigenvalues for these 4 guesses and 3 different eigenfunctions. I've prepared some more examples in the example script, example harmonic eigenvalue. So we look for the eigenvalues of a harmonic oscillator. In this case, of course, the eigenvalues and the solutions are well known, so we can actually check the solution that has been found. The equation is 1 lambda y double prime in line 11 plus lambda times y equals 0. Lam is the free parameter, and we have homogeneous boundary conditions in the interval from 0 to 2 pi in line 14. And to fix the solution, we have to specify one more boundary condition, and I've chosen the slope at 0 should be 1. If we run this script, we see the well-known results. The eigenfunctions are harmonic oscillations, and the eigenvalues are the squares of integers or half integers. So I start with the guesses 1, 2, 4, 6, 10, and we get the eigenvalues 1, 2.25, which is 1.5 squared, 4, which is 2 squared, 6.25, which is 2.5 squared, and 9, which is 3 squared. So this works as expected. We can do something very similar with a pendulum oscillation. So if we look for the eigenvalues and eigenfunctions of the pendulum, we just have to replace the harmonic oscillator by a pendulum oscillator. The equation is shown in line 7. And the free parameter is now the pendulum length. I call it len in the script. And the boundary conditions are the same as before. Len is the length in meters, because we have specified g, the gravitational acceleration, as 9.81 meters per square second. Okay, I use the the boundary condition 0, 0, 0.1, so a small initial velocity of the pendulum. Let's see. Let's run through the script. Actually, the right boundary is not 2 pi, but 6, is 6 exactly. With 2 pi, we get slightly different eigenvalues, of course. So we find for these 5 initial guesses in line 22, we find 5 different eigenvalues and the corresponding eigenfunctions. The shorter the pendulum, the faster the oscillation. The longest eigenvalue, about 4 meters, gives the slowest oscillation of the pendulum. You can try to find more eigenvalues using other guesses for the eigenvalue length of the pendulum. This concludes this video. Thanks for watching. Thanks for listening.